Bonjour, merci d'être venu. Hi, thank you for coming. So, I'm Pierre-Antoine. So, today we are going to see mathematically one of the consequences I explained that was the Goldstone mode, right? When we break a continuous symmetry. So, we will have a mode that restores the symmetry in some sense. So at Q equals 0 for the ferromagnet, it will have zero frequency. And what will be interesting is that if you look at the energy to flip a spin, there's a gap. But if you look at the collective mode that flips a spin, there's no gap at Q equals 0. So that I think that's an amazing thing to see. So we'll see this by computing the transverse susceptibility. And that will lead us to the Mermin-Wagner theorem, and I will comment on the effect of Kanamori-Brückner screening that I discussed in the context of TPSC. Then we move to the electron-phonon interaction that I will do in the simple jellium model. We'll see an effective interaction that's attractive at low frequency. So that's an important aspect of the electron-phonon interaction, is that it is retarded. So that's why we can have an attraction between electrons, because they scatter off a phonon and then the other one scatters later. So they are never at the same place at the same time. So once I have this effective attractive interaction, I will show you how we get superconductivity, or how we get a pairing instability. So we saw with the ferromagnet that we can build a self-consistent equation in the ordered state with the broken symmetry, but we can see the instability coming from the normal state, because we saw from the normal state we had an instability when 1 was equal to u times the single spin density of states. So in the same way here, we will see the instability that leads to superconductivity from the normal state. Okay. So that's the plan. Any question? So next week we will finish superconductivity. Any question? Okay. So let's look at this pairing, transverse susceptibility. So we look then at the up down. So here we have S plus, and here we have S minus. That's why I call this minus plus. And here let's take K plus Q, and let's take K here. So now if we look at the effect of interactions here, we will take this term here, the Fock term, because we're looking at up interacting with down. So that will be given by this. In other words, there's a minus sign here, so I have minus, and then the next diagram is something like this. And then, as usual, this is self-consistent. So I will continue with diagrams like this, etc. Okay. Now I will define the susceptibility, this, with the minus sign here. So I have minus plus, and now I have that the susceptibility, the minus plus, is of Q. This will be all the components is equal to chi 0 minus plus of Q not very good. And then here I have two minus signs, so that's a plus a u chi 0 minus plus square, and then I have the series. Okay, so in the end I have that the chi perpendicular minus plus q is equal to chi 0 minus plus of q divided by 1 minus u chi 0 minus plus of q. Okay. So our task is to compute this chi 0 plus of q. So this is just a product of two Green's functions, and the sum over Matsubara frequencies gives us Fermi functions, as usual. So we get that this is equal to minus 1 over n sum over k of Fermi function of zeta tilde k plus q, and we work with we are in the ordered state here, so we work with our effective Hamiltonian that breaks the symmetry, minus f of zeta tilde of k divided by omega plus I eta plus zeta tilde k plus q minus zeta tilde of k. Now what is this? Let's compute this. Zeta tilde. So I need to take care of the spins here. I forgot. So up, down, up, down, because these are different for up and down. So k plus q up minus zeta tilde k down, and that's equal to so the k, I take again the k squared over 2n as a dispersion relation. So k squared disappears here, so I have the cross term that I will call vf dot q, and then here I have plus u and down and minus and up. Okay, because you remember that for the up spin, the R3 term is and down, and then this is and up. So I have vf dot q minus delta, where I've defined now delta is equal to u times m. In other words, it's equal to u times n up minus n down. Okay. So when even when q equals 0, you see that there is some energy gap between single particle states for up and down. It can be advantageous to flip a spin in one direction or the other, or on the contrary, you need energy to flip a spin from down to up, for example. Okay, so let's substitute this inside here, and we have that this is equal to, perhaps I can move even further down. this is equal to minus 1 over n. And now I will take Q, I will do an expansion here. So sum over K F of zeta K tilde plus Q up minus F zeta tilde K down, and I will write omega plus I eta minus delta, and here I expand because the gap is large, so I can expand 1 minus Vf dot Q over omega plus I eta minus delta plus a term of order Q square over delta square. Okay, we could compute it, but I won't. So now when I integrate Vf dot Q, this is isotropic, and then so when I do the cosine integration, this disappears. Okay, so I am left with minus, what is this? If I sum this over K, this is n up, right? N up minus n down over omega plus I eta minus delta times something that's 1 plus order Q square over delta square. So this is, given this definition here, this quantity is just minus delta over U over omega plus I eta minus delta times 1 plus order Q square over delta square. Okay, so what happens now when I substitute in this expression? So I have to be careful with the denominator. The numerator is not a big problem. So this is minus delta over U divided by omega plus I eta minus delta. And in the denominator, I have 1 minus U times this, okay? So U times this is plus delta over omega plus I eta minus delta times 1 plus order Q square over delta square. And then there's the same term, the Q square is in the numerator also, but this is already big. The denominator is more, we have to be more careful because there will be some cancellation. You see that if I take this omega plus I eta minus delta and I put it here, what will happen? what will happen is that the denominator will vanish here, or not vanish, simplify, I'm sorry. And this one will become omega plus I eta minus delta. This is this. And this is where the miracle occurs, right? I'm so happy I didn't do a sign mistake, a sign error. You see minus delta plus delta, so that disappears. And what am I left with? I'm left with minus delta over u times omega plus I eta minus this term. So this term I will call dq squared. Okay, so this is pretty much it. So you see there was a gap in the single particle excitation, but the collective mode has a pole that where omega goes to 0 when q goes to 0, right? So that's the Goldstone mode. So if I look at the, we said that to get sx squared plus sy squared, I need to add these two things. So if I take the imaginary part of chi minus plus perpendicular plus chi of plus minus perpendicular, this will be what? I will get this first term that will, so when I use the Sokatski-Weierstrass formula to take the imaginary part here, that gives a delta function. The minus will cancel. So I get delta over u times pi divided times delta, times delta of omega minus dq squared. And now what happens with this term? What happens with this term is that you see this will change sign. I mean, this will flip, right? Because I get plus minus instead of minus plus. So what will happen is that it's delta that changes sign. And the delta is a prefactor in front of this also. So the term I will get will be minus pi delta over u delta omega plus dq squared. And as usual, this function is odd, right? That's sx squared plus sy squared, the susceptibility, and it has to be odd, and that's what we see here. It works out, it's odd. Now, if we compute the thermodynamics, so thermodynamic, in other words, the sx squared plus sy squared, but at omega equals 0. What we have is for the susceptibility, so we have integral d omega prime over pi of this, so the imaginary part of chi minus plus perpendicular of omega prime plus chi perpendicular plus minus of omega prime divided by omega prime. So that's the susceptibility, right? We saw for the that's the thermodynamics rule that we saw at the beginning. So let's do the omega prime integral. So what will happen is that you see that it will just be 2 pi times delta over u divided by dq squared, right? I replace omega by dq squared. And here I replace, in this term, I replace omega by minus dq squared, but there's a minus here. So the two terms add up. So this is, yeah, so this is the zero frequency thing. So that's the susceptibility. Now, Mermin-Wagner theorem, you see that in 2 dimensions, if I want to get the fluctuations at the same point, I have to integrate over q, and that will be divergent. Okay, so that's what I had argued with the Mermin-Wagner theorem. And what I want to say about Kanamori-Brückner is just that you see I did RPA everywhere. Now, if we try to do instead TPSC, and so to have all these renormalization that come from the different channels, what you find is that you need to be at a Van Hoff singularity to really get this type of instability. In other words, if you look at 1 minus u spin times the density of states, if you look at this criterion, you find that U spin is, you remember we had that U spin, I mean, it can be sort of approximated by 1 plus lambda U. So when U is large, it's 1 over lambda, and this is like it is like 1 over the density of states. So this is almost realized, but it's not. I mean, the instability on the lattice is at the antiferromagnetic wave vector, not at the ferromagnetic wave vector, unless the density of state has a singularity. And if you have done a many-body, solid state class, you know that if I look at the density of states in 2 dimensions, it can have logarithmic singularities there. And that's when you could have, that's when you can have ferromagnetism. Otherwise, it doesn't work. Now, the other thing you can see is that the ferromagnetic state will become unstable when D is negative. Okay, because then you get a negative susceptibility, thermodynamic susceptibility. And so that's another way to see that where the system is unstable, and usually that coincides with this condition. Yeah. But it could be that it can happen that it does actually on the triangular lattice, that the condition that you get from what happens with the spin is different from the one you got from Mark-Riffock. So it may happen that the spin fluctuations destabilize the ordered state, a little bit like in the case of Mermin-Wagner, before you get to the transition. Okay, so that ends it. Any questions? Okay, now we change topic completely. We move to superconductivity. But before we do the superconducting state, I want to show you how phonons may lead to an effective attractive interaction between electrons. I will do that in the jellium model, which is not very realistic model, but it shows you how it happens. And I'll tell you, once I have done it with the jellium model, I'll tell you how to do a more serious job. So I remind you that in the jellium model, we took a background of ions that was uniform and that did not move. So we will take the same background, but we will allow it to move. So they see there's a paradox now, because if you allow the background to move, it is charged also, and it's a uniform charge, like in the case of the electron. So there would be the natural frequency of the ions, if I look at a fixed electronic background, will be at the plasma frequency, right? The plasma frequency of the ions, different from the plasma frequency of the electrons, but still the plasma frequency. So we need to find out how we can get something more reasonable. In other words, how we can get sound waves with some linear dispersion. And that will come out rather easily with this dielectric function approach. So it's very phenomenological, but it's a nice phenomenology. Okay, what should I do with this? Okay. So we said that the Poisson equation, so I'm looking at this, minus grad squared phi tells us that it's equal to 1 over the dielectric constant times the charge. And the charge has several components. One is the fluctuation of the electronic charge. The other one is the fluctuation of the ionic charge. And the other one is some external perturbation. So this, we Fourier transform first. Then we get q squared phi of q and omega equal to 1 over epsilon 0. You see, I will find an effective dielectric constant that will respond to rho external. So we saw that one way to see the effect of this is to use linear response and use the irreducible part of the susceptibility for rho electron times phi q and omega. So if we put here the self-consistent phi, here we just have the irreducible piece. And then here we have minus the irreducible piece of rho ion phi plus rho external. In linear response, in the case of the response of a scalar potential, there was a minus here. So we can put all of this on the same side, and then we get phi of q omega times 1 plus, now I divide by q squared, okay? Q squared. And so here I will have on the right hand side, I will just have rho external divided by epsilon 0 q squared. On the other end, on the left, rho e is the charge, right? So it's e squared times the e squared times the density fluctuation. And now e squared over q squared epsilon 0 is just the Coulomb interaction. So that's v of q, okay? V of q is E square over Q square epsilon 0. So here I get V of Q times chi irreducible of electron charge, and here I will do the same. So I get plus V of Q chi irreducible and ion and ion. This is equal to this. So now you see, when I put this in the denominator, I have the dielectric constant, basically. So the dielectric constant epsilon of Q and omega is just equal to 1. Okay, I could just put this here. So this is, I have epsilon 0. Epsilon 0 times 1. Okay, 1 plus V of Q, irreducible n E. That's what we found when we looked at Thomas Fermi screening. So this you have to go back to the notes. I will not redo the calculation. This is what we had for, you see, we didn't have the ions, so you understand that this is really exactly what we had for Thomas Fermi screening. Now this piece here is what? This piece is for the ions. But for the ions, the frequencies that we are interested in are large, because the ion plasma frequency is small, because the mass of the ion goes in the, remember that the plasma frequency is n E square over m epsilon 0. So here we have something that's 2,000 times heavier than the electron. So I will write the form of the dielectric constant that was appropriate for the ions. So this will be plus, okay, if I take the same one here and I subtract it later, so I have minus 1, and now 1 plus this as the form 1 minus omega plasma frequency of the ion squared divided by omega squared. Okay, so these ones disappear. Remember, this was the appropriate form, because if you look at the pole, then the pole is at the plasma frequency of the ion. Okay, so that's my new dielectric constant. Now I will show you how we get the acoustic mode. Okay. The acoustic. If you look at this dielectric constant, that's what should go in the denominator. Yeah. When do we have a collective mode here? We have a mode when the dielectric constant vanishes, right? When the dielectric constant vanishes, you don't need some external charge to get some oscillation. So let's look at where this is 0. So I will multiply I will try to find where this is equal to 0. So I multiply everything by omega square. I hope I got this right here. Is this Q Thomas Fermi square divided by Q square? Yes, I think so. I think I did it backwards here. Anybody has the notes? I think this is Q Thomas Fermi square divided by Q square. So if I multiply everything by omega square Q square, I get 0, right? So I can multiply by what I want. So I have omega square q square plus omega square q Thomas q square Thomas Fermi and here I have minus omega I square q square. Okay, because I multiply by omega square q square. And then I look for where this is 0. So this is 0 when I put, if you want this on the left here. So I get omega I square q square is equal to this. So that's omega square. And then q square plus q Thomas Fermi square I will put here. So you see that at small wave vector, what do I have? At small wave vector, I have that omega square is equal to omega ion square divided by q Thomas Fermi square times q square. So see, this is the square of the sound velocity times q square. So we have what we want, right? The phonons, their frequency goes to 0 as q goes to 0. So this is the vibration of the frequency. And now you see that we found an approximation for the sound velocity related to the ion plasma frequency divided by the square of the Thomas Fermi wave vector. And that is called the Bohm-Staver relation. And if you look at simple metals like sodium, for example, so metallic sodium, this is not bad. I mean, orders of magnitude. Okay. So that's the idea for the jellium model. Okay. Is it all right? Now I want an effective interaction between electrons. So the effective interaction is there, right? So let me erase this. So I have that the phi of q omega is equal to rho external divided by epsilon 0 q square and divided by this, okay? So, I mean, by this bracket here, because I just put the bracket there. Now let me do the same thing I just did. I multiply numerator and denominator by omega square q square. So in the numerator, I have omega square q square. And in the denominator, I have omega square q square plus omega square q Thomas Fermi square minus omega ion square q square. Okay. Then I will rewrite this again, and we're almost done. this is rho external divided by epsilon 0. And then I will factor 1 over q squared plus 2 Thomas Fermi squared, which is what the effective interaction when we add just electron. But okay, now this is different. Now I have omega squared, and I have factor q squared plus, so I'm left only with omega squared. And here I have omega I squared divided by this. But omega I squared divided by this q squared plus is the phonon frequency that I will call omega q squared. Okay, so this goes to 0 at 0 frequency, because when I factor this, I need to divide by q squared plus q Thomas Fermi squared. So, and this is the phonon frequency. Okay. So we have this nice result. This is rho external divided by epsilon 0, 1 over q squared plus q Thomas Fermi squared. And this I will rewrite as 1 minus omega squared q divided by omega squared minus omega q squared. So without phonons, that's what I had. Okay. With phonons, I have this. And I made a mistake here. It is a plus. Right? If I put this, I get rid of omega q, then I get this. Now you see what happens if the frequency is near the phonon frequency here, that can, but below, that can become large and negative. So that's how we get attraction between electrons. So you have to be at low frequency, less than this this phonon frequency, but close to it. Yes. Okay, and if you look at large frequencies, very large frequency, you recover the the screened Coulomb interaction. So what are the consequences of this effective attractive interaction? This is the pairing instability. But before I do that, let me just mention how we could do this a little bit more seriously. So we could have a lattice, break the symmetry, have some lattice that has its own modes that are a vibration that comes from, we have the valence electrons that hold all this thing together, and you use the Born-Oppenheimer approximation to get the effective potential between ions, and they would be harmonic oscillators. Okay, and as usual, we quantize these harmonic oscillators, and then what is the effective? How does the effective Coulomb electron-phonon interaction look like? Well, it will be some coupling constant that can depend on Q and everything, and then there will be sum over K and Q of psi dagger K psi of, or let me write C's for conduction electron, and sigma. So C dagger K sigma C K plus Q sigma. So this is the charge density. This is rho electron at wave vector q, right? This thing without the lambda. Now in the lambda, you have the electron-phonon interaction. And here there is the displacement. You will, how will you change the charge density of the ions by having a divergence of their displacement, right? So here you will have some q dot u of q, where u of q is the phonon displacement, and the u of q, you do the usual thing. You quantize these vibrations. Okay. Now you see we can do exactly what we did with the hybridization function. In other words, in the when we write the partition function, there will be trace e to the minus beta h electron, e to the minus beta h ion, and the time ordered product. So we go to have the exponential of minus the integral from 0 to beta d tau of h electron ion of tau. Okay. Where this is basically h ion electron is this. Okay, there are various forms that you can take, but that's a simple one. Now what you can do is notice that if you take the harmonic approximation for the phonons, then you can do what we did with the hybridization function. In other words, we can integrate over the, we can do the trace over the ions, and we will be left with just the connected part here. And this connected part will involve the connected part of the ion. Okay, so there will be a u correlation function, and that's the u correlation function right there. That's the phonon propagator. And this is a density, and then there will be another density because we have the square of this u. Okay, so that's how you would do a more serious job using this link cluster theorem. And you see you could have interaction with transverse modes now if you wanted. Any question? So I won't do it, but this is how you end up with an effective interaction between electrons that is retarded and has a phonon propagator here. Okay. So now we do just like we did in the case of the instability and the spin susceptibility. We will look at the pairing susceptibility. So the instability will be in another channel, if you want, in the particle-particle channel. And now this is where it would be much easier to do the calculation using the Feynman approach. But we will stick with the Schwinger approach, which is quite a mess in the normal state. But it will allow us to introduce the Nambu notation, the Nambu propagator, that is extremely useful in the superconducting state. So we are working a little bit too hard right now, but this will be rewarded by what happens in the superconducting state. So how did we find this instability, this ferromagnetic instability, right? We look at Z of, if you want, R tau, SZ of 0, 0, and we can, we can Fourier transform this if we want, and in the end, the thermodynamic instability is just the integral 0 to beta d tau. And what is this? This is a C dagger up, C up, minus C dagger down, C down. So everything at time tau. And this is the same thing at time 0. So instead here, what we want to see is a pairing instability. In other words, what we will look at is a C dagger up, C dagger down, both of these at time tau, and C down, C up, both of these at time 0. Okay? So instead of being a susceptibility, let's say in the spin, it's a susceptibility in the pair. You see what I mean? And this will be a non-zero in the normal state. There's always this always exists. But with this attractive interaction, this will become infinite at some point. In the same way that we found the spin correlation function to diverge in repulsive interaction. With attractive interaction, we will see that this can diverge. Okay, so that is the plan. Now, how would we compute these susceptibilities here? We computed delta G, delta phi, right? Delta G up, for example, delta G phi, and we combine these things. So the G is a C dagger C, and when we differentiate with respect to phi, we get a C dagger C. And we did the same thing actually in the transverse channel with S plus S minus, but I didn't do it in the Schwinger formalism. Actually, I cheated a little bit. Now, if we want to do this in the Schwinger formalism, you see that we need a Green's function that is a C dagger C dagger. And then functionally differentiate with respect to this phi. So what we will do is introduce this Nambu notation. Psi is psi, or I can write, well, in the notes I wrote psi, so let's stick with psi. Psi dagger down. And then psi dagger is psi dagger up, psi down. So you see, whoops, the other way, I'm sorry. It's a row vector. Okay, these are called Nambu spinners. So they have, let's see, the component 1 of psi is psi up, and the component 2 of this psi is psi dagger down. You see? And if I look at the anti-commutator of psi alpha, psi dagger beta, you see this anti-commutes with this, and this anti-commutes with this. So it's diagonal. So it's delta alpha beta. And otherwise the anti-commute. I mean, it's only when I have a psi dagger psi and a psi dagger psi that I get a 1. So these are canonical fields. They obey canonical commutation relations. And I will finish by writing the Green's function, and we will compute them. We will have, in the Green's function, there will be components like this, and we will compute derivatives. So the Green's function, G, now is a matrix. It's equal to minus the time-ordered product of psi up, psi dagger up. Okay, I can put some time tau here if you want. Tau, there are other indices that we can add later. And then here, what do I have? I have the time-ordered product of psi up. You see, I take really a direct product of this with this, or if you want a tensor product of this with this. So this is psi up, and now I'm in the second column. So the second column is this. So I get psi of tau, psi down. And here I have t tau, psi dagger down. And with the first one is psi dagger up. And I have the tau again. I forgot to put tau. And here I have this, so I have psi time ordered product of psi dagger down, of tau, psi down. So you see that's the usual Green's function here, minus time ordered product here. And this one here is just, I mean, it's not the same. I need to anti-commute and the time will be different. But I have the objects I want. So I will take, next time I will do the rest of the job. Okay? Any question? Okay, so see you Monday.
Thank you very much. See you Monday.
Stick around if you have questions.